In this lesson, we saw how functional equations can be an advantageous alternative to differential equations. We will use a Bean example to show how the classical statement of differential equation problems based on a balance with a differential element can be replaced with the balance of a finite element to get the alternative functional equation. We also will try to emphasize the similitudes of the two resulting problems. It is well known that many physical problems have been represented by models of differential equations, and also that these equations are the result of imposing balance or equilibrium on differential elements, very small. Once this condition is imposed on an infinite set of elements of a certain domain, the well-known traditional model based on differential equations is obtained. If discretized, a model based on differential equation is obtained, which normally approximates the solution of the initial problem. Here, an alternative model based on functional equations is proposed. Consider a non-differential element and establish the balance or equilibrium in it. If the balance must be fulfilled for any non-differential element of any dimension of all of a certain domain, a functional equation equivalent to the previous differential equation is obtained, so that an alternative model is obtained, which appears in the form of a functional equation that is without involving derivatives. This new approach to the problem allows new numerical and exact methods, which may be more efficient than those corresponding to differential equations. Therefore, the problem can be posed in two ways: differential and functional equations. The following section illustrates the method by applying it to the problem of the formation of a static beam. This method is equally applicable to much more complex cases.
The next example is very interesting and surprising. I am going to compare functional equations with differential equations. I am going to show you that practically all problems that we can state as differential equations can be stated also as functional equations. I take the case of a beam just to illustrate this. What is the differential equation of a beam? The differential equation of a beam is just a balance equation. What I do is I take a very small piece of the beam, I remove the sides, and I replace the effect these sides have on the piece by adding bending moments, shear stresses, and also the load and the forces, axial forces. And then I establish the equilibrium of moments, the equilibrium of forces, vertical and horizontal forces, and then I get the differential equation. I get a fourth-order ordinary differential equation.
The balance of vertical forces in the differential piece leads to equation 1, where Q and P are the shear stresses and the load applied to the point X respectively, and the balance of moments gives equation 2, where M is the bending moment at the point X. Consider now the well-known relationship of strength of materials between the bending moment and the curvature of the beam in equation 3, where C is the deflection of the beam at point X. From 1, 2, and 3, the well-known fourth-order ordinary differential equation 4 of the beam is obtained. Calling W to C prime, the rotation of the beam at the point X, from equations 1, 1, and 3, you get the first-order differential equation system in 5, which is the usual model in terms of differential equations when you are interested in the shear Q, the bending moment M, the rotation W, and the deflection C. It is well known that the system 5 of 4 first-order differential equations is equivalent to the fourth-order differential equation 4.
What happens if instead of taking a differential piece, I take a finite piece? I take a finite piece and then I replace the effect of the sides, the same as before. I put the bending moment, the shear, the axial forces, and the whole load on that piece.
In the alternative method, equilibrium equations are established in finite-sized discrete pieces. One of such pieces of length U is shown in the figure, which is an illustration of the balance or equilibrium of a discrete finite piece. The balance of vertical forces in this piece leads to equation 6, where the A function is as in 7. Similarly, the balance of moments leads to 8, where the b function is given in 9. Using the equation 3 of strength of materials, we obtain 10, where the c function is given in 11. In addition, we have 12, where the d function is given in 13.
Then, what I get is a functional equation that I call a fourth order functional equation, which is equivalent in some sense to the previous one, because this has to hold not for a finite piece, but for any piece of any size in any place. So you can see that we can state the problem in two different forms, that I get a fourth-order differential equation and a fourth-order functional equation, and I also can obtain first-order functional equations, as you can see in this slide.
Therefore, we finally obtain the system of 4 functional equations of first order in 14, where the a, b, c, and d functions are those in 15. The system of equations in 14, though it is not exactly the same, can be considered as equivalent to the system of equations 15. Functions a, b, c, d, and f are known as soon as the load p is known. In some cases, the problem can be solved with 1, 2, 3, or all the equations of 14, depending on the boundary conditions. The system 14 can also be considered as a system of difference equations making u equal to delta x, which gives the exact solutions at the discretization points for any value of u equal to delta x. To obtain an equivalent functional equation in C, you can write the last equation of 14 for 3 different values of u and eliminate w, m, and q. For example, if you write this equation for u, 2u, 3u, and 4u, you get the functional equation of fourth order in 16, which can be considered as equivalent to equation 4. Similarly, the following functional equations of third, second, and first order in w, m, and q, respectively, shown in 17, 18, and 19, can be obtained, which together with 16 is equivalent to the first order functional equation system 14. Equations 16 to 19 can be interpreted as equations in finite differences, but it should be noted that they are exact for any value of u, in particular for u equal to delta x. To illustrate how we can work with functional equations, we consider 4 different cases of beams. Assume a beam with uniform load P. Then we have the a, b, c, and d functions in 20, and the system of functional equations 14 becomes 21. With the edges x equal to 0 and u equal to s, the following cases are analyzed. First, the simply supported beam with boundary conditions in 22. Second, the cantilever beam with boundary conditions in 23. Third, the clamp and supported beam with boundary conditions in 24. And fourth, the clamp at both ends beam with boundary conditions in 25. Each of the above cases results in a system of 4 equations in 4 unknowns in the set indicated. These systems are shown in the next tables. Solving these systems and replacing their solutions in 21 with x equal to 0, you get the shear, moment, rotation, and deflection laws shown in the last table. This table gives the systems of equations resulting for each case of beam. This table gives the shear, moment, rotation, and deflection laws for the 4 different cases. In this lesson, we have seen that functional equations is an alternative to differential equations, and that most problems that can be stated as differential equations can also be stated as functional equations. In particular, in the case of a beam, a statement of the equilibrium equations on finite instead of differential pieces leads to the corresponding functional equation. This produces a certain surprise because we are used to state this type of problems in differential form. However, an effort is still pending to obtain the alternative functional equations associated with many other problems. With this lesson, we end our course on functional equations. We have had the opportunity to see a large collection of functional equations together with their solutions and many examples of applications in which these equations appear. I invite you to adopt this alternative as one more for stating and solving the problems you face in the real life. Finally, I want to thank you for the attention and time dedicated to this course.